We are dealing with two dependent samples or matched pairs. So the key concept is testing hypotheses and constructing confidence interval involving the mean of the differences of the values from two populations that are somehow dependent, in a sense that the data consist of matched pairs. The pairs must be matched according to some relationship, such as before and after measurements from the same subject. So that's what we mean by matched pairs. For example, the result of an exam, we take an exam before the review session and then after the review session, and we compare test scores for the two cases.
Good experimental design. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using two independent samples.
Hypothesis test, we use the difference from two dependent samples, that means matched pairs, to test a claim about the mean of the population of all such differences. Confidence interval, we use the differences from two dependent samples, matched pairs, to construct a confidence interval estimate of the mean of the population of all such differences. D, we want to see what each one represents. D represents individual difference between the two values in a single matched pair. Mu sub D, that is the mean value of the differences, D for the population of all matched pairs. Of data, D bar is the mean of those values, just like X bar. S sub D is the standard deviation of the difference, says D for the paired sample data, N is the number of pairs. When the values are dependent, do a t-test on the differences and denote the difference with the symbol lowercase d or uppercase d. Depending on the text, they may use lower or uppercase, and I may use both of them. It really depends on the text, but it's either way is fine. So with that being the case, the mean of the population differences with mu sub d or mu sub d. D is either lowercase or uppercase, and the sample standard deviation, the same thing, S sub d, S sub d, each one is fine. And when that happens, we have the following degrees of freedom is the same thing, n minus 1. We use the lower or uppercase. The formulas are very similar to what we have seen. One of the things that many instructors do when it comes to test of hypothesis and even a confidence interval for this case, they treat the difference as X, and then they do the t-test on X bar mean, if you will, of those. And I'll tell you what I mean by that as we look at a simple example. And what I'm trying to say, there is absolutely nothing brand new. In essence, we are repeating the previous section, but what we do is we repeat it on what? The difference of the matched pairs. So that would be the data that we are interested in. We'll see in a moment. The formulas for T, standard deviation, they're all the same as we've seen before when we were calculating the mean for a bunch of data. If you have a bunch of data, how do you calculate their mean? You add them up, divide by 2. How do you calculate their standard deviation? The same process that you have learned before. Summation of X minus X bar quantity squared over N minus 1, that was the variance. Now instead of X we say D, instead of X bar we say D bar, and that would be the variance. You take a root, becomes a standard deviation. For confidence interval, we would go with X bar plus minus. Now we go with D bar plus minus, where E is T. Remember, it was T S over square root of N, T of alpha over 2. Now it's T of alpha over 2 S sub D, for the, which stands for the differences. And again, lower or uppercase, your choice. The sample data are dependent. That means we're dealing with matched pairs. We are dealing with SRS always. I can't emphasize the importance of that. And the number of pairs, N is large. How large is large? When N is larger than 30. And if that's not the case, then we should have a population which is normal or approximately normal. And this is just like the previous section. It's a robust procedure. So we're going to verify sample data consists of dependent samples or matched pairs. We want to find the difference, and then we basically do the test of hypothesis on those differences, okay? So we find d bar is sub t, and for hypothesis test and confidence interval, use the same t-test procedure used for a single population mean. I can't emphasize this enough. In essence, you make that a simple population mean. It's a simple t-distribution because the hypothesis test and confidence interval in this section use the same distribution and standard error. They are equivalent in a sense that they result in the same conclusion. So I can't emphasize this enough that they are ultimately the same, okay? And so I hope it's straightforward as to what we are doing. Let's look at a simple example to get us.
Cholesterol level change if the diet is supplemented by a certain mineral. 6 subjects were pre-tested and then they took the mineral supplement for a 2-month period. The results follow in the table. Can it be concluded that the cholesterol level has been changed at alpha equals 0.10? Assume the variable is approximately normally distributed, and B, find the 90% confidence interval for the difference between the means.
First, let's understand what is given. We are dealing with the same group of subjects where n is 6. Then the information is given x sub 1 before, x sub 2 after, and now we are going to calculate the difference between the two. For example, if you look at the first one, 210 minus 190 is 20. We're going to do everything by hand here, not that you have to. As you can see on the right side, I have shown you how to use a TI calculator to make life easy. First and foremost, you clear the lists and you put the information in L1 and L2. Now, what is L1 before? What is L sub 2 after? And then when you want to do the calculation, it is L1 minus L2 that you're going to store it in L sub 3 and enter it. And when you do your test of hypothesis, or for that reason, even if you want to calculate the mean standard deviation 5-number summary, remember what we do. We do stats, cat, we select for one variable, type L sub 3, second 3, and calculate. So we do the calculation on L3. So this is done by calculator. So let's do the calculation. We need the difference, we do that. And then if we look at the formula, the difference has to be squared up for the sake of calculating the standard deviation. So after we do that, this is the difference, total of 100. So summation of these 100. So right here, if I want the D bar, so that would be 100 divided by n, which is 6. Now, you do the test of hypothesis on this group. Let me emphasize this. This is now the data that we are concerned with. Never mind the rest. This is the data. Assume there are 6 pieces of data, 20, 65, negative 2, 2, negative 1, and 16, and you're doing your statistics. You're finding the mean, you're finding the standard deviation, you're doing the test of hypothesis, and you're finding the confidence interval for these pieces of data. And for that, in essence, you go to the previous chapter dealing with one sample, and this is the data, and you want to come up with X bar in essence, which becomes D bar. Because when you understand this, you realize this is being repeated now. That's all we need to understand this section. Now, by hand calculation, we do this one also. Now, here's the D bar, simple case, add them up divided by N. Remember, N was given here as 6. Now, standard deviation. When you look at the top formulas for standard deviations, there are 2 ways to do that. One of them is using this formula. You just plug in. We are calculating the standard deviation. You can do it by hand. You can do it by calculator. It doesn't matter. It gives us the formula. Now, If you want to do it with a calculator, the explanation is on the right side, but let's see. I want to show you this one. So L1 minus L2, there is an arrow which stands for store on a TI calculator. You click on that and you are storing after you input L1 and L2 information. And it gives those numbers. Now we are going to do one variable stats. We do the calculation and it gives us those values. Now, needless to say, before even I mention that, this is the one that you need to see for L1 and L2. So first thing first, you enter this. This is your first step, and then this would be the second step and the rest as far as using a calculator. Now, so take a look at the X bar here. That's the D bar. X bar is the D bar, and I'm going to use both cases again because I want to make sure everybody understands. Really, it depends on the text that you're using. Summation of X squared, and this is S sub D. We just simply call this S if we go back to one sample and previous chapter. So the information that is given here, N, if we want to go to that chapter and do the test of hypothesis or anything else, N is 6. So now if I were to use the process, I'm going to say N is 6. This would be the given. X bar is 16.7. S is 25.4. Again, you should use more decimals, but that's not the point here. And I do the test of hypothesis that we have learned in previous chapter. That's what we have here, N, D bar, if you will. We have the S, and so with that being the case, we are going to do the test of hypothesis. All right, so it says, can it be concluded that there has been a change? And again, we don't know, they mean less than or greater than, so that means it's a two-tailed test. And we are taking it to be the claim because we are checking for the change. Remember, mu sub D equals 0, that means no change. Now, if we go back to that chapter, we would have said mu is equal to 0. And mu is not equal to 0. So that's something I want everybody to pay attention to. And so you do the test of hypothesis, you calculate the test statistic. Remember X bar minus mu over S over square root of N. I'll go over that again in a moment. I want to make sure we understand if we choose to go that route, even to use their symbols is okay as long as we understand what we're doing. So plug in, we have everything calculated. And as always, this comes from H sub 0. And it's always 0. Now, we need the critical value. It comes from the choice of alpha. Remember, you're dealing with a two-tailed test. 90% confidence interval corresponds to alpha of 0.1. Alpha is 0.1, and so each tail is 0.1 divided by 2. So degrees of freedom is n minus 1. That means 5. T becomes plus minus 2.015. Now it's a matter of drawing and comparing. So when we do the drawing, we notice that the test statistic is somewhere in between. And so clearly, the test statistic is in between, and simply put, do not reject H0 or fail to reject H0. So if you are not rejecting H0, you are rejecting H1. If you're rejecting H1, then you're rejecting the claim. The claim becomes false, and there is not sufficient evidence to support the claim that the mineral changes a person's cholesterol level. So this is the end of the test of hypothesis, and everything is being repeated. Now, what about the confidence interval? it's the same thing as before. X bar plus minus E. Now it's D bar plus minus E. So you need to calculate the E. E is T S over square root of N. Now it's T S sub D over square root of N. Plug in the same T, the same S, and the same N that we have. Results in the following number. We are going to use the X bar, or in this case D bar of 16.7, and add and subtract this number. When we do that, it results in the following. And as you can see, the confidence interval contains 0. Therefore, same decision, do not reject H0. Remember, every calculation you do, the decision gives you just part A. Then you elaborate by looking at H0 and H1 for the claim, and you do the writing. But your calculation gives the result part A only, and then you do the writing. So part A from your calculation. Let's look at technology. So since 0 is contained in the interval, the decision is to not reject the null hypothesis H0. In other words, the same result. So we are dealing with the t-test. What we are entering for that is L sub 3, which is L1 minus L2. All right. So when we input the data, it results in the following. And the p-value, as you can see, is, by the way, the p-value would be this area to the right of 1.610 times 2. And we have the result for the confidence interval also. We use the t-interval to do that. So we have the test, we have the t-interval. So if you have the data as follows, you calculate their difference, you end up here. So all you have to do, you look at this group of data and deal with those numbers. So this results in n being 6. Because of this calculation, I can say X bar is 16.7, S is 25.4, and I do the test of hypothesis on this one, and test statistic, remember it was X bar minus mu over S over square root of N, and you put it in here. Now mu is given, whatever the number is. In the case of the differences, we are assuming the difference, or mu in this case, is 0. It comes from H0. When we did the test of hypothesis for this part, mu was given, whatever the number was. It wasn't 0 always. But in this case, it is the difference between the two. And the idea is that we have a difference of 0, or we don't have a difference, or in some cases we have less than or greater than, okay, a specific number. So the point being is that it's ultimately the same test of hypothesis, the t-test for one sample. This mu will always come from H sub 0. For the differences, it becomes 0. Let's go to the next example.
Data lists ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the awards were presented. This is a small, random selection of the available data so that we can better illustrate the procedures of this section. Use the sample data with a 0.05 significance level to test the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. Assume the variable is approximately normally distributed.
In order to do that, we need to calculate the difference for each pair. Obviously, it's a matched pair. You're looking at the same year. We're dealing with actress versus actor. And the difference has to be calculated. It is done for us. And this is what I mean. We are dealing with those values. These are the ones that are important to us. The difference, that's all. And by the way, if you do 28 minus 62 or 62 minus 28, it makes no difference. Just be consistent. So which one is the first group? Which one is the second group? We want to, at the 0.05 significance, we want to test the claim that the population of ages of best actresses and best actors, the differences have a mean less than 0. So first we need to find X bar or D bar, add them up, divide, and then we need to find the standard deviation, S or S sub T. S sub D, by now we know we can use a technology or do it by hand. You come up with X. Now, remember what this says, less than 0. So you have the first one taken care of. Mu sub D is 0. Mu sub D is less than 0. That's H1, and that is the claim, and that is a left tail test. So we write the test statistic, T equals D bar minus mu over S over square root of N, or S sub D. And again, mu sub D comes from H0 is 0. And the result is negative 1.557. All right, so what happens next? Critical value, alpha is 0.05. Degrees of freedom is n minus 1. This is a very small sample. 1, 2, 3, 4, 5. So 5 minus 1. And we get to the value of the T for the left tail test. So we do the drawing and we compare the two numbers. The test statistic is not in the rejection region. So you do not reject H0. And when you don't reject H0, that means loosely put, you reject H1, that means you reject the claim. What does it mean when you reject the claim? The claim is false. And then you do your writing. So do not reject H0. The claim is false. There is not sufficient evidence to support the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. There may be other ways of putting it. There is not sufficient evidence to conclude that best actresses are generally younger than best actors, however you want to put it. So, well, as far as the p-value is concerned, I want to show you right here. The p-value would be this one. This red shaded region is the p-value. You can see clearly is larger than alpha 0.05, which is the green shaded region. So you have to read that from the table or use the technology to get that. And remember, because it's a t-distribution, it's a limited table. But conceptually, you've dealt with that, so it shouldn't be a big deal. So having said that, this is the same question. We're not going to repeat that. Everything is there. We want to calculate the p-value. We want to calculate the confidence interval and so forth. I mentioned it in the previous page where the p-value comes from, the area to the left of test statistic, which is negative 1.557. So this is the area. If you use the technology, it gives you an answer. But if you go to the t-distribution table, and we've done it a number of times by now, you should be comfortable with that. So you look at the row with degrees of freedom of 5, -1, or 4. And test statistic is negative 1.552. And it corresponds to an area in one tail that is greater than 0.05. The p-value is not there. We can just tell that is larger than 0.05, everybody, okay? So it is larger than 0.05. The technology gives you 0.0973. In a moment, I will show you how we arrive at that using a table in case. But for now, let's stick with that, and let me show you the confidence interval. So for the confidence interval, basically, remember the confidence interval was x bar plus minus e. Now it's d bar plus minus e. We have the d bar from the previous page. We need to calculate the e. E was t alpha over 2 s over square root of n, or now it's t alpha over 2 s sub d over square root of n. So we have those calculated from the previous page. We put it into the formula for it. It results in the following. D bar or x bar, add and subtract this number. It results in mu or mu sub d being between negative and positive. Negative 24.2 less than mu sub d less than 3.8. It contains 0 and it gives you the same result. Since 0 is contained in the interval, the decision is to not reject the null hypothesis. H0 mu sub d equals 0. So we have 90% confident that the limits of negative 24.2 years and 3.8 years contain the true value of the mean of the age difference. By the way, of course, one thing you may notice, negative 24.2 in an absolute value sense is a lot larger than 3.8 in an absolute value sense. It is tending towards negative, but nevertheless, even if on the right you have only 0.1, 0 is still there. Okay, so according to this data, you cannot reject H0. Quickly look at the t-table. Here's the t-table. Degrees of freedom was n minus 1 or 4, and the number was 1.552 is in between. Area in one tail is larger than 0.05, less than, according to this table. And that's exactly what we got. But I just want to make sure that, again, we've been exposed to reading the table. Using technology, using table, you come up with the same result. So clearly p-value is larger than 0.05, and you therefore come up with the same decision as you made here. Do not reject H0. Let's go to the next example.
A sample of 9 local banks show their deposits in billions of dollars 3 years ago and their deposits in billions of dollars today. At a 0.05, can it be concluded that the average in deposits for the banks is greater today than it was 3 years ago? Use alpha is equal to 0.05.
We basically need to calculate the difference and then calculate x bar or d bar and s or s sub d. So that needs to be calculated. You just subtract the third from the second and you do the math. So this part, you have to go through the process. So you're going to use technology, or you're going to do it by hand. Makes no difference. You have the calculation. Here's the answer. So let's move on. So with that being the case, we want to see if this is greater. You can say that 3 years ago was less. So mu sub d is less than 0. Left tail test. Let me be clear how we arrive at that greater today. You have two choices. If you subtract the third from the second, it becomes left tail test. If you subtract the other way around, the second from the third, it becomes greater than. So at a 0.05, can it be concluded the average in deposits for the banks is greater today, is equivalent to say, was the deposit less 3 years ago? So it's equivalent to saying, was the deposits less 3 years ago? They are equivalent. And that's what we are doing, because we are saying the first row, in this case really the second one, we're going to subtract the next one from it. So it's 11.42 minus 16.69. That's what we are using. If we do it the other way around, then we have to calculate it for the case where mu sub t is larger than 0. So what happens is, if you go that route, I want to make sure everybody understands that one too. If you go with greater than, what happens to your calculation? Can anybody tell me what would be the difference in this calculation if we go with today minus 3 years ago instead of 3 years ago minus today? So what we have here is 3 years ago minus today. Okay, that's how we've done this calculation. Can anybody tell me those numbers, d bar and s sub t, If we want to calculate for today minus 3 years, what we would get?
A positive number?
Beautiful. Same number, positive. D bar is positive 1.081. What about S sub t? What would that be? What's going on with the variance? Nothing. It's identical. Why is that? Take a look at the formula. Summation of D minus D bar quantity squared. It doesn't matter which one comes first, you're going to square it. Because of that, they stay the same. And that's extremely important for you to understand, the concept of a variance. It doesn't look at which one comes first. It's just looking at the mean of the differences. Okay, the sum of the mean of the differences. Okay, that's how it's the weighted average of that. And that one will have the same value either. Okay, so having said that, the next thing is to calculate test statistic. You see the formula at top, you plug in. So we get negative 1.674. And the critical value comes from the choice of alpha, which is 0.05, and t, or degrees of freedom, is n minus 1, 9 minus 1, or 8. And you compare, as you can see, negative 1.674 is way into the non-rejection region. Do not reject H0. So the claims, there is not sufficient evidence to support the claim. So there is not enough evidence to show that the deposits have increased over the last 3 years.